In this video, we discuss constant pressure calorimetry. Calorimetry is a technique that is used to measure heat. And because heat at constant pressure has a direct relationship to the change in enthalpy in a process, then we can use constant pressure calorimetry in order to be able to determine changes in enthalpies in reactions or in any other chemical process. Alright, so we're going to set up here a numerical example that will allow us to explain what constant pressure calorimetry is. Here's how the device looks like. You're going to have some sort of container in which you're going to have your reaction. Alright, and generally the way that this is going to work is the reaction will work in aqueous solution. So most of what you have inside the calorimeter will be actually water. There will be a few solutes dissolved if this is an aqueous solution, and then the reaction between the solutes might be exothermic or endothermic, and that's something that you're going to be able to detect because you will be measuring changes to the temperature of the solution. Right? So something that is key to this problem is to have here a thermometer that tells you how much the temperature of that solution is changing upon reaction. Now, this is going to be a constant pressure device, so what that means is that the volume is not controlled. You're actually under constant external pressure, and that means that the container has to be somehow open. Now, the other thing that has to happen here is that this calorimeter has to be adiabatic. What adiabaticity means is that no energy will be lost to the surroundings. Okay, so however much heat we actually generate in this reaction, right? The heat from the reaction will be going entirely into the water that is forming the solvent of that reaction. Okay, no joule of energy produced during the reaction as heat will be lost to the surroundings, and that's something that is quite important to the design of the calorimeter. So how do we do this operationally? Well, what you would like to have here is some insulated walls in the calorimeter that kind of guarantee that all of the energy stays inside the calorimeter for a given amount of time. In practice, what you can actually do is use two nested styrofoam coffee cups, and that is actually a remarkably good constant pressure calorimeter. Okay, when you have two nested coffee cups, the amount of energy that is released to the environment, at least initially, is very small. And what that means is that, again, no energy is lost, and you're going to be able to track the changes to the energy in the reaction or the enthalpy in the reaction by simply measuring the change in temperature in the water. Right, so here's going to be our applied problem. We're going to be mixing hydrochloric acid, HCl, with sodium hydroxide. Okay, so this is a strong acid, strong base reaction, which is exothermic. It generates energy as heat. And we're going to be mixing 100 mils of each at concentrations 1.0 molar. Right, so notice that the total volume will be 200 mils, and the approximation is that most, if not all, of that volume will be water. Okay, these solutions are reasonably dilute. That means they mostly have water. So for the purpose of the calculations, we're going to assume that this is exactly all pure water. Okay, so here's the key concept in calorimetry. There is a chemical reaction taking place, HCl in aqueous solution plus NaOH, to generate sodium chloride, which is a salt, and water. Right? And that reaction is going to generate some heat. It's an exothermic process, so energy will be transferred from the reaction into the surrounding environment, right? But because the energy has nowhere to go other than to the water that is surrounding the environment, then every single joule of energy produced by the reaction must be absorbed by the surrounding water molecule. Okay, so this is exactly the same thing as to say that all of the energy released by the reaction is absorbed. Okay, that's why you have a negative sign there, by the calorimeter, which in this case is simply just the amount of water that you have, right? So, or is caused by the water that you have. That will be the heat absorbed by the water. Okay, so for the specifics of these problems, what we have is that before we mix those reagents, they are at exactly the same temperature of 24.60 degrees Celsius. And then after the reaction takes place, after we mix this, the temperature rises, okay, because energy has been released from the reaction into that water of the calorimeter to 31.30 degrees Celsius. Right, so the question then would be, please calculate what the change in enthalpy in the reaction on a per mole basis would be from this data. Okay, and something that is provided here as well will be the heat capacity of water under constant pressure, and that is 75.29 joules per mole Kelvin. All right, so notice that because we have the change in temperature in the water, and we have the heat capacity at constant pressure of water, we actually can determine what is the heat absorbed by the water. Once we determine that heat absorbed by the water, then we will just change the sign, and that will be the heat released by the reaction, and then we'll just simply have to calculate how much that difference in enthalpy it is on a per mole basis to calculate the change in molar reaction enthalpy. Right, so let's start first with the amount of energy as heat absorbed by the water. All right, so because this is a heating process, then the equation that you need to use is just the number of moles times the molar heat capacity of the water times the change in temperature. Right, so let's think about the moles then. Notice that in this case, the total volume of water that you have is 200 mils. Okay, here we're going to assume that the density of water doesn't change appreciably with temperature, which is not true, but this is an approximation. And the approximation also is that this density is about 1 gram per milliliter exactly. Okay, so that will be 1 gram per milliliter, and this is exact, and again, doesn't change with temperature. That is a little bit of an approximation, but it suffices for the purpose of this problem. Right, so what this allows us to do is change the volume into grams of water. Okay, and then from here, we can calculate the number of moles simply dividing by the molar mass. So for every mole of water, there are 18.02 grams of water. And what this means is that our number of moles is equal to 11.1 mole. Okay, so now we have the number of moles. We also have the molar heat capacity at constant pressure of water. And then we just need to calculate the change in temperature. Okay, here you can do this in Kelvin, which is recommended, or in degrees Celsius, because the the difference between those two temperatures are actually the same. And you can find that just simply taking the difference between those two numbers, you will get here to a 6.70 Kelvin difference in temperature. Okay, so that is how much the temperature increases. So we're actually then ready to punch in the numbers and calculate what this heat absorbed by the water is. All right, so that will be 1.11 mole multiplied by the heat capacity of the calorimeter, 75.29 joules per mole Kelvin, and then the difference in temperature, which is 6.70 Kelvin. And what this results into is an energy absorbed as heat of 5.60 10 to the 3 joules. Okay. Notice that that heat is actually positive because it has been absorbed by the water. Okay, so then from here we can calculate what the heat released by the reaction would be simply by changing the sign. Right? If about 5.6 kilojoules have been absorbed by the water, okay, that means that 5.6 kilojoules have been released by the reaction. Okay, so that means that the reaction is exothermic, and right away we can say that Q of the reaction is equal to minus 5.60 10 to the 3 joules. Okay, so this is our first calculation, and this is the key step. The fact that in a calorimeter, those two things are the same, just with opposite signs. All right, so the last thing then is to actually take this and then calculate enthalpies. Okay, so let me erase all this to make sure that we make room for the rest of the problem. Right, so notice that because we're working at the constant pressure, what we can actually do is this. Right, notice that the change in enthalpy is identical to the heat transferred to the energy transferred as heat at constant pressure, right? And because this is actually at constant pressure, then we're actually ready to calculate what the reaction enthalpy would be, right? So delta RH will be QP of the reaction, but that is exactly what we have calculated. So this number is simply minus 5.6, 10 to the 3 joules. Okay, we're almost done. There's just one more step left, and that is to recognize that the problem is asking me about the change in reaction enthalpy per mole of reaction. Okay, obviously, this energy that we have calculated here, this energy as heat or this change in enthalpy, that depends on how much reaction you have going on. Right? It would not be the same to mix 100 mL and 100 mL than to mix 1 liter with 1 liter. Right? The second process, where you have more reagents, would actually lead to a much larger release of energy as heat. Okay, so we would like to normalize this on a per mole basis, right? So calculate this per mole of reaction. Right? So the way to do that is simply to proceed as following. The molar change in enthalpy of the reaction will be the change in the enthalpy of the reaction that we have calculated here divided by the number of moles of the reaction, and this is important. Now we're looking at the reaction, we're no longer looking at the water, right? So this will be the moles of the reaction. Right, so then we have here two reagents, and notice that when you do the math, right, that is going to be equal to 0.100 mole, this is going to be equal to 0.100 mole. So looking at the stoichiometry, it's obvious that you have a 1-to-1, so there's no limiting reagents in this case. The reaction is actually using the right stoichiometric amounts, and then the overall moles of reaction that we have right here will be 0.1 moles. Right, so then our final calculation would be minus 5.60, 10 to the 3 joules over 0.1 mole, right, is going to give us minus 56.0 times 10 to the 3 joules per mole, or the preferred unit of energy in when we calculate reaction enthalpies will be kilojoules per mole. This will be equal to minus 56.0 kilojoules per mole. Okay, that is your final answer for this problem. Alright, so in this video we have introduced the concept of calorimetry, which is a way to calculate or determine the change in enthalpy in chemical reactions or in any chemical process. Okay, so we've been able to go through the strategy to solve these problems and illustrated how you can calculate the change in reaction enthalpy for an acid-base reaction, all right, by using calorimetry as it's intended to be.